we've introduced the atom to you, we've been lying a little bit less each time, right?
Yeah, so we're going to lie a little bit less today.
So we talked last time about the Bohr model of the atom, which is essentially a nucleus and these electrons orbiting around the outside. And we even talked about the idea that there are waves somehow imparted in this as well. We're going to look at the atom with something called the quantum theory. You want to talk about that for a second?
Remember that we said in the last video that there'd like be 21 levels, and we said that's not true, and we pointed at the iron spectrum. And now we want to say there's sublevels and levels on the sublevels. So it turns out there are 4 different kinds of sublevels. Remember we said they were like shapes. So the first shape, what's the first shape?
Well, this is a sphere. Now, we don't call it a sphere.
We call it a S.
An S-shaped orbital. So S for sphere kind of works up nicely.
And that notice there's just one of these. And then the second set of sublevels are the P sublevels. And they kind of look like dumbbells, like if you're lifting weights, right? Sort of, kind of, maybe not. But notice that there are sets of 3. What's the next group?
These are d orbitals. And d orbitals come in a set of 5. And what you need to be aware of is each of these lobes, that's the location where an electron can be.
So actually, technically, a probability distribution.
Which we'll talk about, where an electron can be found 96% of the time, I think it is.
Yeah,
something crazy.
And then the most complex one are the Fs. And of the Fs, they're crazy, aren't they? Cool shapes, by the way. The Fs, there are 7 sets. You might have noticed that the S's, there's 1 set, the P's 3, the D's 5, and the F's 7. So 1, 3, 5, 7. So that's what the orbitals are, but there's actually sublevels. Take it away.
So I don't want to confuse us all too much, but there are 7 main energy levels. Can we all agree on that? So even though Bohr was not really correct with how he viewed things,
he wasn't wholly wrong either.
He wasn't entirely wrong. He said there's 7 energy levels. So I'm going to just draw these number 1. And each energy level has more privileges as you go along. Now remember, we said as we talked a second ago, there's 4 different shaped orbitals.
S, P, D, F.
S, P, D, F. I learned it as small people die first, but I heard that that's offensive, so we'll just say stupid people die first, which I think is offensive to
small.
Stupid people. So I don't know what we're going to say.
So
here's what we're going to do. In the first energy level, we can have S-shaped orbitals only.
Only S's.
That's it. And what you should be aware of in advance of this is that orbitals can only take 2 electrons maximum.
Right.
So if we have a set of p orbitals, which are 3 orbitals, right?
That's 6.
That's 6 because each one can
3
take
times
2
2.
each, right? So in the second energy level, we can take s orbitals and we can take p orbitals. But this is a set of p orbitals. So altogether,
notice it's 2p because he's in level 2, and it's 1s, 2s, 2p.
So what that means is that this number right here just tells us which energy level the set of orbitals is in. We know that s orbitals always come in a set of 1, p orbitals come in a set of 3. This number in front just tells us where they're located. Now, in case you're wondering here, third energy level is going to have an s.
3s, 3p.
Have a set
Now
of
we
Ps.
add the next level.
And
3D.
a set of Ds. And to make this a little bit less time consuming, you're going to see that it keeps on going as you go. Now, there's actually theoretically G orbitals and H orbitals. We're not going to get into those, but I'm going to show you the quickest way to draw one of these tables if you want to use it. We're just going to go like this. Everything down this row here is going to be P's. Everything in this row, the column is going to be D's. And these are all F's. Now, what this means is that each of these energy levels has a certain number of electrons they can hold.
So there are lots and lots of energy levels. I mean, you could count them all up. It's way more than 21.
Correct.
Right? Or actually, 21 falls. Because if they can fall from 7D to 7P, 7D to 6D,
There's a lot. There's a lot. The other thing we want to be aware of is this. In general, the first energy level, so let's say we made a line right here, is less energy than the second energy level. Is less energy than the third energy level, et cetera, et cetera.
And remember when I was falling down the stairs, then electrons want to live at the lowest energy level. So, but they fill in a kind of a weird pattern. So what's the pattern that they fill?
Here's what I propose we do here. We're going to pretend that we are lords of the atom, right? And we're going to give each other a group of electrons. We're going to say put them into the atom. Now, if I gave you the chance to put electrons in the atom and you wanted to create a happy atom, where would you put those electrons?
Bottom, lowest level.
The lowest energy levels
Which
possible.
would be like the 1s. That's the lowest level. Even though it's on top, don't worry, that's the lowest level because it's a level 1.
Now I'm going to show you a trick here because it doesn't, if I were doing it, if I were the one who made up the atom, I'd go everything in the first energy level, then the second, then the third, then the fourth, and the fifth, and the
But it
sixth.
doesn't quite follow that.
It doesn't quite follow that way. So I'm going to show you a little arrow diagram, and if you follow the arrows from the tail to the head of each one, it's actually going to fit how we put electrons into orbitals.
So we do 1s, 2s, but then 2p, 3s, 3p, 4s. So folks, what we want to do is let's just take like a simple atom like helium. So once you write helium helium has 2 electrons. And so we're going to have a notation. We call it the box notation. So why don't you write the first box that we
So we call it the box notation, but it's also known as the orbital notation. And what we do is we write a box for every single orbital that exists.
And then we write underneath the box the name of the orbital. And the first one is simply 1s. Now, since helium has 2 electrons, and each orbital, or in our case, box, can have 2 electrons, he would have 2 electrons in it.
And the way we do this is kind of weird. And we do these little half arrows which show 1 electron going in and then the second electron.
And the reason is because actually the electrons are spinning in opposite directions. So the arrow actually means something. Not that important. You just need to know they go up and then down. So next up, let's do a different atom. Let's do nitrogen with its 7 electrons.
How do we know that there's 7 electrons, by the way?
Because he's element number 7, which means he's atomic number 7. He has 7 protons, which means he also has 7 electrons.
So we're going to follow the order here, right? So the first orbital we're going to put into is the 1s.
Box number 1, 1s, right? Orbital number 1, 1s.
And how many electrons can we put in there?
2 electrons.
So we're gonna go
So I'm
1,
trying to like get up to 7. I want to fill up 7 electrons. The next level is 2s orbital.
2s.
And 2s, of course, is still one box for the 2s, and that's 3, 4. Now the next level is crosshatchy ball game, 2p. Now with the p, this is interesting. Remember we said there are 3 different orbitals for the p, so he makes 3 boxes together and writes 2p underneath that whole set of them. Now we need to put the electrons. Now how many more do we have? We got 4, we got 3 more
left
electrons.
to place in here.
Now here's a tricky thing you got to do. You don't actually put them in the first box. Since each orbital has the same amount of energy, you put 1 in each.
So when we're placing electrons in, we go 1, 2, 3.
Now why do we do that again?
Well, because again, each of these orbitals has the same amount of energy, and if we put 2 in any one, it's going to make the other 2 unhappy.
Right. And this is called what?
This is called Hund's rule.
And the Hund's rule says that if you have
A set.
a set of electrons or set of orbitals, you put 1 in each before you double them up.
Yeah, it's kind of like, do you have any siblings?
I do, 2 siblings.
So let's imagine it's Christmas, and there's 3 of you, right? It works a perfect example. And your parents say, John, we love you so much, here's a present, right?
Yeah.
And then they say the second, we love you so much, here's a present.
Yeah.
And the third, we're like, nah, let's give John a second present. How is your third brother gonna feel?
Not too happy.
Not too happy. Won't that be a really unstable, unhappy arrangement?
Yeah.
And the same thing works here. This right here, where each of them has 1, is a much more stable arrangement than if this one had 2, this one had 1, and this had none.
Now, one other thing we should say, Mr. Dmitrowicz, is how else do we write this? Besides 1s, there's a kind of a notation. What would we write?
Well, this is called orbital notation. There's also something called electron configuration. It makes it a little easier because this right here is 7. Can you imagine doing it right now for 100?
Yeah, it'd be a lot.
It'd be a lot.
So helium, instead of just writing this box notation, orbital notation, we can also write what?
We can also write it like this. We can write the orbital, and then we can write the number of electrons we put as a superscript on the top.
So it's 1s2.
2.
Now on this one, this bottom one, you would say 1s2, 2s2, and then 2p, 1, 2, 3.
Now, the nice thing about this is it's quicker to write it like this. It doesn't show us quite as much information of where electrons are in the atom, but I prefer writing this than this because I can get all the information I want from this.
So, Mr. Dmitrowicz, let's do like crazy one. Bromine with 35 electrons.
I'm getting tired just thinking about it, writing this all out, but it's 35 electrons.
Okay, so first level is 1s, right? And we got the box with the 2 electrons. Okay, the 2s box.
By the way, we're
with
just
2
following the
electrons,
arrows, right?
Yeah. So 1s, 2s. Now we're going to go to 2p, right? Now 2p, remember, has 3 boxes. Notice they're the same level, so we draw this one shape. Put 2p underneath, and then we're going to fill it one at a time, though. So you got to do 6,
1,
2, 3, 4, 5, 6. Now, right now, we're up to 10 electrons.
And you may say, why do we bother putting 1 at a time? It just out of good practice, because eventually we aren't, like right now, you know we're going to have more than 10, so we could just put 2 in each one. But
We've got to get to 35. So the next level is the 3s orbital. So that's just a simple little one boxer deal. There you go. Now we're at 12. Now go to 3p. So the p orbital with the 3 boxes, 3. And then 3p.
1, 2, 3, 5, 6.
Probably a new line. After 3p, we hit, now this is intriguing, we go to 4s. So we go 4s.
This is the first hiccup that we have, because normally you think, oh yeah, the 3D is part of the third energy level. Just so happens the 4s has less energy.
And 2 electrons.
2 electrons in there.
So right now, we are at 20, right? 20 electrons. If you were to add that up through 20, we had to get to 35. Now we jump over to the 3D. Now, remember the d orbital has 5 orbitals, so it's like a big long line with 5 boxes. There you go. And then put 3D under there. And then we got to fill them up one at a time. That's going to be a total of 10, right? So, but 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 10.
So that takes us to 3D. Where do we go after the 3D?
4p.
The 4p. So
Another 3-boxer ball game, right?
here's
Now,
our-
this is where we get interesting, because right now, if we did our math, and you might notice my eyeballs are looking, I'm looking over at the periodic table. We're going to talk later about how that kind of works. We have 30 electrons. If we were to add those all up, we're at 30. So for 35, we have 5 more to give. This is the last orbital box. So what would you do?
So we're going to put 1 in each one. Again, this is according to Hund's rule.
5 more to give. Right?
1,
2, 3, 4, 5. And that's it. That's 35. And now we want to write it in the regular sort of electron configuration notation. So you would write first
You can
one,
kind of follow
1s2. You see that from the first box. 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p5. That's long. But what is this? This is like the address of all 35 electrons when they're in their ground state. Now remember, the electron can still get excited. That's how we make light and waves and all the stuff we talked about earlier. But this is in their ground state. This is where all the electrons have an address, for lack of a better term.
And just real quick, as you take a look here, it is really important you follow the arrows here, because if you put first into the 3D, you are not putting electrons in the lowest energy orbital. So we're going to go from the 3p to the 4s and then to the 3D. So here's the thing, even this right now, it's kind of lengthy, right? So there's got to be a shorthand way, and we're going to talk about that later. And we're also going to have a much better way than doing these arrow diagrams. But for right now, when we practice, you're going to be filling in these charts, and you're going to do either orbital notation, or as Mr. Bergmann likes to call it, box notation, and you're also going to have to do electron configuration notation. See you next time.